Alright, so chapter 14 is going to take a look at the compositions of solution, characteristics of solutions, and various properties that are impacted by the concentration of these solutions. We've already talked about a few of these this year. We've talked about molarity, moles of solute per liters of solution. We've talked about mass percent, just basically percent composition, part over the whole. Mole fraction we have not talked about, but it's very similar in terms of looking at the moles of one component over the moles of the entire solution. And then molality is our newest concentration, and that's going to be the same as molarity with the solute moles on top, but we're going to only compare it to the kilograms of the solvent as opposed to looking at the whole solution. Because molality is based completely on quantities as opposed to volumes, it is independent of temperature, whereas molarity is dependent on temperature because of how volume changes in response to it. So pretty much what we have to do is just be able to convert between the different concentration units based on what we're given. Here we're told an antifreeze solution is 40% ethylene glycol by mass, so that's telling me 40 grams out of every 100 of the solution is ethylene glycol. I'm told what the density of the solution is, which will allow me to relate the volume of the solution to a mass. And we're going to use these two pieces of information, along with perhaps molar mass, to calculate molarity, molality, and the mole fraction. So molarity again is moles of solute per liters of solution. So the 40% concentration gives us the mass of that solute per the mass of the solution. To get to moles, we're going to need to convert grams to moles. And to get to volume, we're going to need to use our density because that will relate mass to volume. So if you calculate the molar mass of ethylene glycol, you'll get that it's around 62.08 grams. That takes care of the numerator. That gets us to moles of solute. Our density will help us get to a volume unit for solution, which is what we want for our molarity. A centimeter cubed is equivalent to a milliliter. So if there's 1,000 milliliters in 1 liter, there's 1,000 centimeters cubed in 1 liter as well. So we now have the units we were desiring for molarity. We multiply the numerator, divide by the denominator, and we get that we have a concentration of 6.77 molar. We're next going to take a look at molality. If our solution is composed of 40% ethylene glycol, and we have 100 grams of solution, and 40 of it is ethylene glycol, then 60 of it is water. And because we need just the solvent on the bottom, we would have to do that kind of math, looking at the pieces making up the total, to get our starting points. So our numerator will still be 40 grams, but our starting point for our denominator will now be 60 grams, so that we have the solute and the solvent in the right places. If we remember from the previous slide, molality is moles of solute per kilograms of solvent. So I need to do the same thing that I did with molarity, convert grams to moles. And now all I need to do is take the grams of water and convert it into kilograms, using 1,000 grams equal to 1 kilogram. Multiply across and I get that this is 11 molal. Notice the little m as opposed to the big M. Molality plays a big role in determining the concentrations of salt solutions that are placed on bridges and roads in order to keep us safe in the wintertime. So we'll talk about that a little bit more in the second video. Finally, we want to calculate mole fractions, which means we need to have the moles of the different components. We can't calculate the moles of the solution, but we can calculate the moles of both the solute and the solvent, and then combine those together to give us the moles of the solution. So if you go through and take the 40 grams of ethylene glycol and divide it by 62.08 grams, you will get that that has 0.644 moles of ethylene glycol. For the water, we would take the 60 grams of water and divide it by its molar mass, 18.02. And if you do that, you'll get that you have 3.3 moles of water. So when that math is completed, you will get that you have a mole fraction of 0.16. And that is saying that 0.16 of your mixture by moles is ethylene glycol, and therefore 0.84 moles of water is, or the 0.4 is the ratio of water by mole composition in your mixture. If you need to pause, I would do so now. Okay, I pause this to make it a little easier to read the question. This time we're going to calculate both the molarity and the mole fraction. We're given the molality of our solution of acetone, CH3COCH3, and ethanol, C2H5OH. We're also given the volumes of both components of our mixture. And we are allowed to assume the volumes are additive, so if we find the volume of one component and the volume of the second component, we can find the total volume. And since we're given molality, which is the moles of the solute acetone over a kilogram of solvent, we would need to find the volume of both pieces to find the volume of our solution for molarity. So if you take that there's one molal, of acetone, that's saying that there's 1 mole of acetone for every 1 kilogram of ethanol. So I've converted my moles into grams, because in order to get volume, I'm going to need density. And density can only relate back to mass. I can use that mass of acetone divided by the density to get me my volume of acetone, 73.7 milliliters, since a centimeter cubed is equivalent to a milliliter. I will do something similar to get the volume of the ethanol. 1 kilogram of ethanol, I'm going to convert from kilograms to grams. And now I'm going to use my density to get from grams to a volume to get 1,270 milliliters of ethanol. Why we wanted to do this, and I should have said this before, I apologize. Remember that molarity is moles of solute, which we can get pretty straightforward from molality, per volume per liter of solution. So we needed to find the volume components of both pieces to be able to find the total volume of my solution. So I can add those two pieces together and then convert it to liters. So here I've got 1 mole of the acetone divided by the total volume of my mixture. And now I'm going to convert from milliliters to liters. And when I do the math through, I will get a molarity of 0.746 molar. To get the mole fractions, I'm going to need to find the moles of each component. Acetone's pretty straightforward. Ethanol, I'm going to have to find the moles using the molar mass. And so I went ahead and just started with ethanol. I already had the moles of acetone. 1 times 1,000 gives me 1,000 grams. That gives me 21.7 moles of ethanol. So now to calculate my mole fraction of acetone in this solution, I would take, hopefully that's a little better. I would take the moles of my acetone and divide it by the moles of both the acetone and the moles of ethanol to get the moles of my solution. And when I do that math, I get that I have a mole fraction, which is very tiny, of 0.0441. So if you need to pause, please do so now. The next thing we're going to talk about is how you determine whether a solution forms or not. And the key idea is that you want to have similar polarities because you need the energy of the solution formation to be exothermic compared to the energy of the actual breaking up of the two components to allow space for the solute to interact with the solvent. And if you do have similar polarities, you're more likely to find ones that have similar intermolecular forces that can hydrogen bond. You're also more likely to find substances that can form ions. And the more similar the substances are with one another, the greater the likelihood that they will be able to form a solution more readily. So again, I told you there's a couple steps involved. First, the solute's got to give room to allow the solvent to go in between it. The solvent also has to do the same, and then the two have to be able to mix together. And in order for this to be spontaneous, we want to have an increase again in entropy from back in our chapters for thermodynamics, and we tend to like our solution enthalpies to be exothermic, that energy is going to be released. So in this question, I'm asking you which of these solvents, water or hexane, would be used to dissolve the following substances. With sodium chloride, we know it's an ionic compound, which means it's very polar in nature, and so it's going to choose to dissolve itself in, well, it will dissolve in the more polar solvent. Hexane is symmetrical in terms of the 6 carbons all singly bonded to hydrogens, so that is more of a non-polar solvent. Water, having the 2 lone electron pairs, is very polar, and so water will dissolve salt. Water also has hydrogen bonds, as well as hydrogen fluoride. They both have a hydrogen that's attached to N, O, or F. So the polar HF molecule is much more likely to dissolve in water than it is in hexane. Octane, however, contains 2 additional carbons and 4 additional hydrogens compared to hexane. So it too is extremely nonpolar. It only has the London dispersion forces available. And so these two will dissolve in each other more readily because they are more similar. Ammonia is a polar molecule with a lone electron pair on nitrogen. It also can hydrogen bond because of that nitrogen atom connected to hydrogens. And so it interacts very well with water, and that's what it will dissolve with. Now CH3COOH, I want to show you the structure of this. And so if we take a look, we see we have the double bonded O, we have the OH, and then we have the CH3. That OH is able to be protonated. It's able to interact with the water, and as a result, although it does have some nonpolar characteristics, it is more polar because of that OHN, and so it is more soluble in water. In the compound that falls below it, that's very similar to it, it ends in a methyl group. It's more of an ester, carboxylic ester, which has carbon groups on both sides of the double bonded O and the single bonded oxygen. The 2 methyl groups kind of protect the rest of the molecule from the 2 oxygen atoms and makes it more difficult for them to dissolve in water. So hexane is a better choice when you don't have that free hydroxyl group, the OH, compared to just methyl groups, carbon groups attached that are by themselves would be nonpolar. So for the next one, I'm asking you to tell me which would be more soluble in water. The one that's going to be more soluble is going to be more similar to water. Remember, water is polar. Water has hydrogen bonds. It has dipole-dipole and London dispersion forces, but the hydrogen bonds are the strongest. So if you have one that can also hydrogen bond, you're more likely to find it in that. And if that's not something they have in common, you want to look for polarity. Here we have NH3 and pH3. Both NH3 and pH3 would make trigonal pyramidal geometries. They're both polar with a lone electron pair on the nitrogen and respectively the phosphorus atom. However, NH3 can hydrogen bond, and that's going to increase its solubility in the water. Okay. CH3CN or CH3CH3, so this is methyl cyanide and then ethane. Ethane is extremely nonpolar to carbon atoms. There's nothing about that molecule that differentiates itself. So it's going to pretty much have London dispersion forces working. Whereas with the methyl cyanide, we have, I think it's also called acetonitrile. We have a triple bonded carbon between the C and the N, and then we have the single bonded carbon to the second. I'm sorry, I'll draw it. It makes more sense that way. So here's our C. Let's try again with a different color. Okay, sorry, start it back up. So there's C. There's the C in the middle. There's the triple bonded N. And then now we have H's coming out. Not as good at this as I used to be with the school pad that I think Maddie may remember. Okay, so we have a symmetrical area on this side of the molecule. We have a very asymmetrical area on this side of the molecule, so this is a polar molecule, and that is more similar in structure to water than the 2 carbon groups that are single bonded with the 3 hydrogens attached to each one. So CH3CN is going to be a better choice for dissolving in water. Finally, we have CH3COOH and CH3COOCH3. I just talked about this one on the previous slide, and we saw that the OH group allows that to be more soluble compared to the methyl group at the end. So if you need to go back and look at those slides, just kind of move the video back a little bit.